Hello. This video is for strong and weak acid and bases. And so today we're going to be looking at what strong and weak acids are. We're going to look at some different theories or different ideas about acids and bases from some different scientists. And we're going to kind of explore the particle views of acids and bases and what those atoms and molecules are actually doing when we put them in solutions. Okay. So we're going to kind of start off where we left off in the last video, where we looked at a group of acids and a group of bases and looking for trends. So here we have a table of some common acids, and you might have some of these like cola and vinegar at your home. And so if we look at all 5 of these, we want to look for any patterns that we see. And so again, this is kind of based off the last one, but we can look at how all acids are made up of nonmetals. That's making up the majority of these substances. And this includes carbon, oxygen, and chlorine, just to name a few. And those are all forming covalent compounds, right? And if we look at the chemical formulas here, if we look for something that they all have in common, the one element that stands out is hydrogen. So when we are looking at substances, an indicator that we are looking at an acid is if there's hydrogen or there is a hydrogen on it. And if we look at these, all of them except for acetic acid on the bottom, all of them have a hydrogen in the front. Okay, that's an indicator that this substance is an acid. Okay, and then the last one is that they all break apart or dissociate, which is going to be a common term that we will see later in this video. Okay. In a solution, so they're breaking up. The molecules are becoming smaller polyatomic ions in the solution, and they're going to be making at least a H+ ion, right? We see that on the left-hand side here. We have at least one H+ ion in each solution, as well as an anion. Right, anions are the negative charge ones, and each one we can clearly see has one of those in there. Okay, so again, we want to look for indicators in formulas to determine if solutions are acidic or basic. So we're going to do the same thing again, this time a table of bases, and we're going to try to find 3 patterns that all of these have in common. So for one, they all contain one metal, and a hydroxide ion, which is our OH minus. Okay, and the metals we see are all found in the first 2 columns of the periodic table. Oops, should say columns. All right, and then the last one, and this is going to be a little odd, but if we look at the right-hand side, so we see sodium hydroxide, for instance, NaOH. We have a positive cation and an anion, and that makes the molecule on the left side. But if we look at something like ammonia here, we see it's made up of NH3, and the ions that form from that are NH4+ and an OH. Now, looking at this, you might be kind of wondering or confused because there's no OH in this molecule. And we're going to kind of address that. So how can that be if there's law of conservation of matter, anything that we can't add or create new elements. So where is that oxygen coming from? We're going to talk about that a little bit more in the Bronsted theory of acid and bases below. But that's going to be one of our patterns, is that some compounds, such as ammonia and sodium carbonate, which is found below here, some of these compounds, when dissolved, form or create OH minus ions in the solution. So create's probably not a great word. We're going to strike that. Because again, law of conservation of matter, we're not creating hydroxide ions. We're actually using the oxygen in water molecules to create those hydroxide ions, or to form hydroxide ions using those oxygen elements. Okay, so also we can see, just a fourth one, not all of them have the word hydroxide in it. Some of them do, but ammonia and sodium carbonate do not. So we can't use their names as an indicator as if it's an acid or a base. Okay. So that kind of leads us to our two theories for the acid and bases. So the first one is called the Arrhenius theory of acids and bases. And so we're just going to run through these. And so he defined acids as a substance that adds hydrogen ions. To a solution. And then he defined bases is a substance that adds hydroxide ions, or OH, to a solution. Right, so that's fine and all. It doesn't explain why up here, this predicament that we have, how do we still have hydroxide ions forming from a molecule that doesn't have any oxygen in it? And that leads us to Bronsted and Lowry theory of acid and bases. And so they wanted to tackle that idea. Okay, so they're similar in that they're both involving protons and hydrogens, but they're just dealing, like, it's kind of semantics. They're just using different words to kind of articulate their message a little clearer. Okay, so Bronsted and Lowry, their acid definition is a substance that can donate a proton. So a proton is just a hydrogen ion, right? So really the acid definition is the same. It's just we're saying a proton instead of hydrogen. Tomato, tomato. It really kind of clears up our base definition, though, where acid doesn't change so much. So a base is a substance, according to Bronsted and Lowry theory, a base is a substance that can accept a proton. So one is giving, one is donating. Okay, so if we go back up real quick to our list of acids, Bronsted and Lowry are saying these hydrogens are all being donated, or can donate a hydrogen or a proton, and bases are molecules that can accept those hydrogen ions or can accept those protons and form, using water or whatever solution they're in, to form a hydroxide ion. Okay, so really just be careful when you're thinking about the two of them. Arrhenius, he's talking about hydrogens and hydroxides. Oops. So H plus and OH minus. Bronsted and Lowry, they're talking about protons, donating, and accepting. Right? If we want to boil it down to some key phrases, that's a good way to do it. So if we look at this solution of ammonia, we can see that ammonia is in a solution of water, right? It's an aqueous solution. And so one hydrogen ion is actually going to go and donate to the ammonia. So if we had to label in a chemical equation which one is the acid, which one is a base, because really in any equation you always need one acid or one base. You need one donating and you need one accepting. So in this case we lose a hydrogen ion or we move it to ammonia. So ammonia is accepting that proton, so that's going to be the base. Hydrogen in this case is an acid. We'll see also how water can be both an acid and a base, depending what substance is in that aqueous solution. So in this case, water is an acid, and then we can see that we have a cation, ammonia form, as well as a hydroxide ion. And that kind of leads us to this idea of strong and weak acids and bases. So if we take a look at these particle views of two different substances, we have hydrochloric acid on the left, and we have formic acid on the right. Not much you really need to know about them, just that hydrochloric acid is a strong acid, and formic acid is a weak. And what that means in a particle view is that when we put this hydrochloric acid in there, the H and the Cl, so we can see the Cl is the teal spheres, H plus is the white ones. When you put hydrochloric acid in water, they dissociate completely. So that's going to be our definition for strong acids and bases, substances that dissociate completely. Okay, none of them are still together, right? They're all forming ions, one positive, one negative. Okay, and if we look at some examples of strong acids and strong bases, this is true for bases as well. They're strong bases, they're dissociating completely. Some examples include hydrochloric acid. We'll write these out. Nitric acid. And then talking about strong bases, we have sodium hydroxide. And barium hydroxide. All right, so strong acids and bases, they are dissociating completely. Okay, so the further we get away from that 7 on the pH scale, the further over here and here we have strong bases and strong acids. Okay, weak acids and weak bases, as we can see in this particle view of formic acid, a weak acid is one that only partially dissociates, because if we look at this solution, HCOOH, that substance is still maintained in some of the solution, right? Only parts of them are getting dissociated. So a weak acid and a weak base are substances that partially dissociate. All right, so if we look at some examples, we have formic acid, which was the one we just saw up top. We also have, let's see, acetic acid, also known as vinegar, which you might have at your home. That is CH3COOH. And looking at some weak bases, let's see, we have ammonia, NH3, let's see, yeah, forgot the M, ammonia, NH3, and this other solution called aniline, which is C6H5NH2. All right, so big idea, strong acids and bases are substances that dissociate completely. Weak acids and bases are some that only partially dissociate. So the worksheet is below. I'm going to skip through the first three, and I just want to take a quick look at question 4 here. So it says label the substances listed below as acids and bases. In each case, list the ions you would expect to find in the solution. So for the first one, well, really for all of these, you want to go to our patterns we've seen for acids and patterns we see for bases and determine which one it kind of applies to. For the first one, hydroiodic acid, we have hydrogen and iodine, and those are both nonmetals, so we're going to see that that's going to be an acid. We also have the word acid in it. We also have a hydrogen in it. All three things point towards this being an acid. So label it an acid, and then list the ions. Well, we know we have H+, right? And then our iodine is going to form a minus anion charge. All right, so that's just kind of an example. You can do the rest on your own. So that was strong acids and bases.